Let's wait for a couple of minutes for others to join. Okay, let's get started. So, I'll share the screen. And of course, the first question is, are there any questions about the material we discussed yesterday or MPI in general? Okay, not really. So let's continue with collective communication. So what did we do yesterday? We talked about peer-to-peer communication. So one process that's sending a message to another process. Both processes, of course, are involved. We have a sender, we have a receiver. And we talked about different modes of communication, synchronous versus buffered, and blocking versus non-blocking. And those two are orthogonal. And this is something that we'll see again, well, at least the blocking, non-blocking part in collective communications. But let's first talk a little bit about the basics of that. So basically, collective communication is communication that involves multiple processes. So basically a group of processes. And a collective communication routine has to be called by all members of that group of processes. So for instance, we saw two examples yesterday. We had broadcast. We'll see another few examples now, scatter and gather. What you also might want to do is to compute a global sum or global maximum or something like that. And also, there's also neighborhood communication in a virtual process grid, but that's something that we'll discuss later on. Okay, so essentially, why do we do this? Because at the end of the day, what's the point? I mean, if I want to broadcast something, well, it's rather straightforward. The only thing I have to do is have all processes, the one that has the value, do a receive, and you do a for loop from the on the process that has the value, and that does sends. So essentially, what's the point of having a broadcast? A separate routine for that? Well, there are a few reasons, of course. If you would have to do any of such common operations based only on peer-to-peer communication, then of course that would blow up your code considerably. And that's something that is a very common pattern, so why not put it into a function of its own, MPI bcast. Okay, so yeah, that's one motivation, convenience for the programmer. But there's actually another thing going on under the hood, and that is that collective communication will also offer you the opportunity, well, not you, but the developer of that library, offer the opportunity to actually do certain optimizations. And maybe I should illustrate that immediately, because I don't think there are any slides on that, if memory serves. So let's start board. Okay. All right. So what we want to do is, let me put process 0 here. And these guys here are process 1, process 2, process 3, process 4, and process 5, 6, and 7. Okay. I'm putting process 0 a little bit at a separate spot because it has a value. And it wants to broadcast that value to all other processes. So, of course, as I mentioned, you can trivially do it by having 1 up to 7 do receive and 0 to do 7 cents. That would perfectly work. And that would mean, of course, that the scaling of doing a broadcast, or that broadcast would scale with O n, where n is the size of your communicator. And that may or may not be acceptable, but the question is, can we do better? Is there a way to improve this so that we can actually do that with in a shorter time? We will have to send 7 messages at the end of the day. That is something that we can't really avoid. But we can actually do something a bit smarter. So what we might do is say, okay, I'm going to have 0 send a message to 4. So now 4 also has 42. Okay. And now both 0 and 4 are going to do the same thing. What 4 is going to do, it's going to send to 6. And 0 is going to send to 2. Okay. So at this point, 0 has sent 2 messages. Okay. 4 has sent 1 message. Okay. Now, next level, 0 is also going to send a message to 1. 2 is going to send a message to 3. 4 is going to send a message to 5. 6 is going to send a message to 7. Okay, so in total, 0 has sent 3 messages. 1 didn't do anything. Yeah, okay, it called receive, but it didn't send any messages. 2 sent 1 message. 3 didn't do anything, no sending of messages. 4 sent 2 messages, and 5, 6, 7 respectively 0, 1, and 0. So as you can see, the number of messages, the maximum number of messages that's sent by the same process is now equal to 3 rather than to 7. Okay, so that's reduction by half, you'd say. Yeah, that's nice, but it's actually better, because what is actually happening here is that we are using a tree, a binary tree, to do the communication. And that essentially means that what we see here, these numbers, is in fact the depth of that tree. So if I really represent that as a tree, then 0 is going to send to 1, to 2, and to 4. Okay, so this is going to send. Okay, and then 2 is going to send to 3. 4 is going to send to 5 and 6. Oh, that's bad. 6, and 6 in turn is going to send to 7. Okay, so that means that what I'm interested in is the depth of this tree. And basically that means that this will be logarithmic in n. So we go down from ON to log n. And indeed, 3 happens to be log with base 2 of 8. And remember, n was in our example equal to 8. So of course, for very small communicators, this doesn't matter. But suppose we have 1024 processes. So now take n is 1024. Then of course, the time this requires if we use such a tree communication pattern is going to be log base 2 of 1024. And that of course is 10. So we have a difference between, on the one hand, a linear implementation, which would in this case take 1024 messages sent by, okay, 1023 if you want, sent by the same process. And now only 10 messages need to be sent. At most 10 messages need to be sent by any process. So that's essentially a reduction of a factor of 100. So this is obviously quite an improvement, and something that you can do if, of course, you have a nice, well, if you are an MPI library developer, then that's something that you can do and should do in order to give good performance to the user of your APIs. So it's not only a matter of convenience, it's actually mostly a matter of being able to do some nifty optimizations. And of course, you could argue that, yes, you could do them yourself as well. But yeah, can you really? Because, of course, how this works, how efficient this is in part determined by the hardware implementation of your communication network. And there are different topologies, and depending on the topologies, you have to make choices where to send your, let's call it seed messages, so that they can actually be forwarded to other nodes that are close to the one which you send it to. So a library, a good MPI library, can take the topology of your network into account. And that is something that, of course, you can do, but then you would have to change your entire implementation, if you would do that point-to-point, you would have to change your entire implementation each time you switched to a cluster with a different communication network. And that would be very unpleasant. Okay, so yeah, okay, there is actually a slide on this. It's probably a one, but okay, basically that is what I just explained you on the whiteboard. So some characteristics of collective communication. It is of course a collective action over a communicator. You always need a communicator, and if you're using a communicator, all members of that communicator, all the processes in this communicator need to participate. That is very important. They must call the collective routine, and of course, obviously the same collective routine, and they must do it in the same order. Synchronization may or may not occur. That depends on whether it is that depends on the specific collective routine. Okay, so on any communicator, that's what I said. Basically, you always have to ensure that the order in which all the processes call the collectives is the exact same for each process. Okay, there are no tags, so basically in this case it's more up to you. So there is no overtaking here. You can't really filter. You can't really say, okay, I'm going to switch the order of what rank 0 did in all the other ranks because I have tags and I can filter. No, that does not exist in collective communication, so you don't have any tags. And non-blocking versions have been added in MPI 3. So for each message, and that's an important rule, the amount of data sent must match the amount of data specified by the receiver. So basically, you really have to make sure that this matches. So it's forbidden to provide receive buffer count arguments that are too long and obviously not too short. So basically that means that in a collective operation that all buffers are same type but also same count. And that was not required, of course, with point-to-point communication. There the receive buffer could be larger than the send buffer. Here, no, they all have to have the exact same length. Okay. Okay. So basically, what the last sentence says about MPI for pi is that given if you're sending arrays, then of course the buffer size is in fact known, and then you don't need to specify them explicitly. They can just be derived from the array. Okay, so the first collective, and I already mentioned the one you hopefully only use for debugging or for very specific timing operations, is MPI barrier. And it just takes a single argument, which is essentially the communicator. So that is something that you normally don't need, because essentially all synchronization is actually handled by data communication. So essentially a process can't continue before it has the data that it needs. That's guaranteed by collective communication. So do you need that for synchronization? Well, typically no. It's not very useful. Of course, if you use it for debugging, and that can be a very good use case, then make sure that you remove it in production, because you will regret it. Extra barriers are basically bad for performance. And in profiling, you would do that in order to profile specific parts of your application, and then of course you can use MPI W time in order to measure. So what you would do is MPI W time barrier MPI W time. So essentially that's the idea. Okay, so more interesting then is MPI broadcast. And as I already mentioned, some process, and that's referred to as the root, has some values that it wants to communicate to all other processes. So MPI broadcast takes a buffer, a count, a data type, the root, and the communicator. So that's the same for C and Fortran. And in Python, actually, we don't need to specify too much. The root will by default be the process 0, which may make sense. And there's something wrong on this slide. Why is this int here? This is weird. Okay, not sure what Wolf has in mind here with the int, but maybe indicating that root is an integer, I'm guessing. Anyway, so it's quite simple. We just need to provide the buffer and potentially, if non-zero, the root. So any process can be the root, but of course, all the processes have to call bcast with the exact same value of root, with a buffer that has the same count everywhere, and data type is the same everywhere, and obviously the same community. And remember, all the processes have to call this. So after the broadcast, all the processes will have the values in their buffer. Okay, and in this case, the root is 1, so that will be the sending process. So here's an example of the call. We have a buffer, the length, which is 3. It happens to be sending characters around, and we have as root 1. Okay, so that's a very simple operation. Another operation which is also pretty common is that we actually have a value that we want to send to specific processes. So we want to send an individual value to each of the individual processes. Again, in our example, root is equal to 1. So basically, it's process 1 that has the values. Okay, so now we have a send buffer, and we have a send count, a data type. We have a receive buffer, receive count, and data type. Then we have the root, and we have the communicator. So this is an MPI scatter. These values are going to be scattered into the receive buffers of each of the processes. So basically that means that process 0 will get A, process 1 will get B, process 2 will get C, etc. So as you can see, the values are simply sent, scattered to each of the processes. That means, of course, that our send buffer must be at least as large as we have values. Sort of, because what is happening here, of course, is that the data count is actually the count of the message we're going to send. So in this case, it's maybe a little bit counterintuitive, but the send buffer, of course, has length, in this case, 5. Okay. However, we're talking about messages, so the message length is 1, and it's sending an individual MPI character. So every process needs to specify the send buffer, but it will be ignored everywhere except for the root. So what is in there doesn't really matter at all. Okay, so at the receiving end, of course, we need a receive buffer, and that will, of course, be just a single character. Again, we have 1 here and MPI character. This is the root and MPI convert. So the root also has a receive buffer. It sort of, if you want, sends a message to itself. How that is done exactly is, of course, up to the implementation. So it could be that it's a memory-to-memory copy. It could be that it's an actual message that's being sent. Of course, any intelligent MPI library will do a memory copy. Okay, so basically for Python, we have MPI scatter. Again, as usual, 2 versions, with uppercase and with lowercase. The uppercase uses a buffer, and of course then you also need to specify a receive buffer. And again, we have a root. Or if you send objects, and then of course the received object is just going to be the return value of the scatter operation, and then you don't need to set a receive buffer, because yeah, it doesn't make sense. It just creates a new object. Okay, so basically very common operation, and one that is very useful. All right. So this remark here I already made. The send count describes a single message. So don't confuse it with the size of the buffer. It's just the single message which is going to be sent to each of the specific processes. Okay. The opposite operation is a gather. So in this case, everyone has a value. We have the same example. Each process has a single character, and it needs to be gathered in the root. So again, the root is 1. Each process has a send buffer in this case. They should all have the same size. And then we've got, in our function call, we have the send buffer, send count, and the data type. Then receive buffer, receive count, and the receive type, the root, and the communicator, as usual. So after the call, sorry, the root will actually have all the values. So basically that means that the root, of course, will have to provide enough storage space in its buffer to receive the size of the communicator messages. So again, just like before, the receive count is describing the incoming message, not the size of the receive buffer. You see it here. Again, we have the send buffer at each process, and the size is 1. It's 1 MPI character. Then we have the receive buffer. Again, 1 describes the message being received, not the size of the receive buffer, and count and type, the root, and so on. So obviously, the receive buffer is again completely being ignored by everything except for the root. So depending on your application, normally you would have here data structure that is allocated dynamically. So with a malloc, a new, or an allocate in Fortran, in order to ensure that you have the right size. Because at the end of the day, the size of the receive buffer depends on the number of members of your communicator, and that's something that you don't know at compile time. Because if you would know that, it would mean that you can only run your application with a given number of processes, and that's of course not what you want. You want to generalize that. So this is typically something that is going to be dynamically allocated, and of course that only needs to happen in the root, because all the other processes don't care. And of course, I could have made the same remark for scatter. It's the same thing with the send buffer in the root. That is typically going to have the size of the number of participants in our communicator. So again, that is likely going to be dynamically allocated. Okay. Of course, again, in Python, we have similar things. The capital verb has a send buffer and a receive buffer. Of course, the receive buffer needs to be large enough. If we have a receive object, then basically that is going to be a list of all the things that have been gathered. Okay. So we can do an exercise on gather. Go to chapter 1. So let's have a look what we are doing. It would actually be nice if the exercise were described here. Okay, so basically the idea is that we are going to have values generated in each of the processes, and that could, for instance, be a short array, let's say 2 elements, and then we are going to gather that in the root, and the root is going to print the entire array. Okay, so let's turn to our editor. That's not an editor, that is my file browser. Okay, so let's just call it gather without too much trying to have too much imagination. So let's do a C example, for instance. Gather.c. So basically up to this point, I've just initialized the local data. So each process generates 4 numbers just to check that everything is all right. and it will just be the numbers essentially from the rank times data size. So 4 consecutive numbers. So for instance, rank 0 would have 0, 1, 2, 3. For process 1, it would be 4, 5, 6, 7. Okay, so everyone generated the data. So now we can do the collective. Let's set the root to 0. Can be anything, but whatever. And then, of course, we need a receive buffer. But let's do that dynamically. So essentially, we want an int pointer receive buffer. Okay, so the MPI gather in this case has data as its send buffer. The message itself is going to be 4 values, so the size of that array. Then the type is of course MPI int. The receive data buffer is only allocated in the root. Remember, it's going to be ignored everywhere else. So essentially, just set it everywhere else. And then the data size is of course the same because it's about the message, not about the buffer. And it's MPI int. We have the root, which we just set to 0 in this case, and MPI world. And then of course, if you're the root, you've got all the data, so you're actually going to print the receive buffer, and we should see consecutive numbers here. So let's see whether that works. No. What did I do? Ah, yes, malloc is a bad idea. I have to also include stdlib.h. That is correct. And of course, what is a bad idea anyway is that I'm not testing whether this actually works or not. But okay, let's forget about that for a second. I'll add it later on. Okay, much better. So now let's run this. Say with 4 processes, then basically we should get all numbers from 0 up to 15. And that's indeed exactly what we get. So that's fine. Of course, I'm very unhappy here because this doesn't do any error handling. And if we're to do that for a very, very large data size or whatever, then this malloc might fail. Any dynamic memory allocation has the potential to fail if no memory is available. So I should actually check. If receive data is null, then we are going to abort. Okay, so this is also a little bit new. If you say, well, okay, I have an error from which I really can't recover, and then of course, what you can do is say, well, okay, I'm going to stop the application. I'm going to stop the application, and you can do that in MPI just by calling MPI abort. You do that over the entire communicator. So basically that means that all processes will actually receive this abort, and they will also sort of gracefully finish processing. So they will gracefully terminate. And that's the first argument. The second argument is 1, and that is actually the exit status. So that is what you would get if you were to query $question mark after running the application. Okay, so this time with error handling, not that it makes a difference, but basically because this is very unlikely to fail. So here it's just an academic example, but still in production code, of course, you would always have to verify that whatever you allocate dynamically, that it is also properly allocated. You would have to do that in C, C++, and Fortran. Obviously, if you use a malloc, a new, or an allocate. Okay. I think this is fairly straightforward. In C, in Fortran, it would be very, very similar. So, do you need more time? Do you want more time, or should we continue? If you want more time, let me know. Otherwise, I'll switch back to the slides and we can have a look what else we can do. How come 16 values are received? Well, the data size is 4, so each of the processes generates 4 values. And that means that these first four numbers were generated by process 0. The next 4 numbers from 4 to 7 are generated by process 1, and from 8 to 11 by process 2, 12 to 15 by process 4. Now 4 processes here, and P is equal to 4. Each generates 4 values, and hence I should get 16 values in total. As you can see here, now I have 2 processes. So the first process again generates 0 to 3, the second 4 to 7. If I would have 8 processes, then of course I would get 32 values, and generated by each of those processes. So the last process with rank 7 would have generated 28, 29, 30, and 31. Let's go back to the code. So indeed, we are, for each process, initializing data, and that data size is fixed. So that's just an array on the stack, and we are initializing it based on my rank. So for rank is equal to 0, that would mean that we have data 0 equal to 0, data 1 equal to 1, data 3 equal to 3. So that is what happens in process 0. In process 1, my rank is 1. So 1 times data size is 4. So that means that data 0 is equal to 4. Data 5 is equal, data 1 is equal to 5, data 2 is equal to 6, data 3 is equal to 7. And this we do for all ranks. Okay. Now, in the root, we want to receive 4 values from each process. So the message size, the message count is data size. Also for the messages we're going to receive. Okay. And our send buffer is data. So of course the root needs a receive buffer. What's it doing? It's allocating one of data size times my size. Okay, data size is 4. My size is of course the number of processes in our MPI indicator. So basically that means if I run this with 4 processes, then we will have data size is 4 times my size is 4, so that's 16, times the size of an integer, because malloc takes values in bytes. Size of int gives me the number of bytes for an integer. So that would typically be 4. So in total, we have 64 bytes, malloc 64. That is cast into an integer pointer and assigned to receive data. If malloc succeeds, receive data is the address of this chunk of memory of size 64 bytes. If malloc fails, if there's not enough memory, then receive data is going to be null. If it's null, then I need to do some error handling. My error handling is simple. I'm just going to MPI abort with exit status 1. Okay, then we've got our MPI gather. So in each process, we have the individual send buffer that has size 4 and MPI int as type. Okay. Everywhere we have to specify receive data. So for all processes except for the root, that's going to be null. Nobody cares because MPI gather is not going to look at it, except in the root. But in the root, it has sufficient space to store 4 times 4, or 4 times the number of processes, integers. So that's good. The message size, which it will receive from each individual process, is of course 4. The type is MPI int, and we specify the root. And then, of course, in the root, we have the data. So now we can also print it, and we just iterate over all the values that are in the receive data buffer. And we will have 4 times the number of processes of such values. So data size times byte size. And then we just print the values. Okay, and of course, at the end of the day, since we did a malloc, we'd also have to do a free. And of course, we only need to do that in process 0, because that was the only process which actually did the malloc. So remember, if you do a free, if you do a malloc, you need to do a free, but of course only in the process where you did the malloc. Okay, more or less clear? Okay. All right, so let's return to the slides. Basically, okay. Now, the can do an advanced exercise basically by introducing some load balance, but maybe let's skip this now. Okay, and let's continue with the global reduction operation. So, what we often want to do is, for instance, compute the sum of values. And then, of course, that means that we need to get some values from each process. And then we want to compute an overall aggregate of that of those values. So, for instance, process 0 contributes D0, process 1 contributes D1, etc., etc. And what we want is to apply this operator. This little circle is intended as an operator. We want to apply this operator to all of these operands. Okay, so that can be either a single variable or it can be a vector, essentially an array if you want. There are some mathematical properties which this operator must have, and of course the one which it should have is associativity. So basically I can first do, for instance, D0 and D1, and then D2, and that should give the same result as first doing D1 and D2, and only then adding D0. So the associativity is a very important property, because otherwise this is of course not going to work. So examples of this are global sum or product, and of course addition and multiplication are associative. It's not a problem. Compute the global maximum or the global minimum. Again, that is an associative operation, no problem. And you can also do user-defined operations yourself. So you can define them, but if you come up with a user-defined operation, make sure it's associative. If it's not associative, it's not going to make any sense, and you will not get the results you want. So, of course, I said that multiplication and addition are associative, and that's of course true if we're talking real numbers in the mathematical sense. Obviously, if we are talking floating point operations, then of course they're no longer associative. So essentially they are, in good approximation they are, but of course results differ. And actually I have a real world example of that where that went, and I'll discuss it in a minute. But let's maybe first talk about what the MPI operation, the MPI collective call looks like. So again, we have the notion of a root, because the root is going to be a process that does the aggregation, or that gets the value that is aggregate. So we have an in buffer, and we have a result buffer. And then we have the message count, and we have the type of the values. So probably not too many surprises here. Then the operation, so in this case it would be a sum. We specify the root and we specify the communicator. So for instance, here is an example in Python. We create a send buffer, and as you can see, that's an NP array, okay, with a certain value. Okay, then we have a receive buffer that can be empty. Why would we initialize it? It's going to be initialized by the reduction call. And then we have MPI world reduce with the send buffer, the result buffer, and the operation which we want to carry out, which in this case is MPI sum. And again, root will by default have 0 as a value. Okay. And then the result, of course, will only be placed in the result buffer of the root process. So what this is going to do is it's going to compute the sum of the values which are held in each of the processes, and the root will actually get that value. Okay, so besides MPI sum, we have a couple of other operations: MPI minimum, MPI maximum, no surprise there, MPI sum, MPI product, MPI logical AND, MPI binary AND, logical OR, binary OR, logical XOR, binary logical XOR, binary XOR, max location and min location. So max location and min location give the maximum and the location of the maximum. So it's perhaps a more interesting operation than max and min, but a little more involved. Okay, so visual representation. Each guy has values. So process 0 has ABC, process 1 has DEF, etc., etc. And the root again is 1. So each one has an in buffer and a result buffer. So after the operation, process 1 is going to have the sum, if we are doing a sum in this case, of A, D, G, and N in its first element of the receive buffer. It would have B plus E plus H plus K plus N in the second element of its receive, and so on. So basically all of that goes here, That goes there, etc. Okay, no, it's not being shown, but you see where this is going. So basically, each element is the sum. So this is an element-wise sum, or an element-wise aggregate in general, of the values held by each of the processes, including the root. The root is the only one which will actually get the result afterwards. Okay, so that's your MPI reduce. You can create your own user-defined reduction operations. So that is with operator handles, and of course we have a lot of predefined ones, which were 2 slides ago, the MPI sum, the MPI product, MPI min, etc., etc. If you need your own, then ensure, of course, that it's associative. Otherwise, it's not going to work. Then you have a user-defined function that performs the operation vector A, vector A, and vector B. And the syntax of the user-defined function you can find in the MPI standard. Then once you have your user-defined function, you can register it. So that is done by calling MPI op create. So create an operation. You specify a pointer to your function. The type of that is MPI user func. Okay. And then we have an integer, which essentially, as you know, in C and C, well, in C, we don't have booleans. Actually, yeah, we do have them in C99, but okay, hardly anyone uses them. So basically, in C, that would mean that 0 is false, anything else is true. So we can specify additional information, whether apart from associative, our operator is also commutative. So that means, is A operator B the same as B operator A? If that's the case, that helps for optimization. So essentially, you would specify that if you know it's mathematically true. Okay, and then of course that should be assigned to an operator handle, and that is MPI op as type, and you give the address of such an operator. So in Fortran, it's very similar. Commute, of course, would be a logical rather than an integer. Okay, so we can do the same thing in Python. So specify a function, whether or not it's commutative, and that's essentially all we need to do, because we get a operation object back, so it doesn't need to be passed as an argument. Okay, so that's the way to do that. So there are quite a lot of other reduction operators around. So one of them is MPI all reduce. And basically that means it doesn't have a root, so everyone gets the result of the reduction. Okay, then there is MPI reduce scatter block and MPI reduce scatter. So essentially the result factor of the reduction operator is scattered to the processes into the actual result buffers. So you can view that as sort of a concatenation, or well, let's say first you do a reduce and then you do a scatter. That's essentially the idea here. Okay, that can be convenient at times. There is also MPI scan, so that's a prefix reduction, and that means that at each rank, it's also a rootless operation. In each rank, you're going to have the in buffer from rank 0 to rank I, so reduction of that. And then there is X scan, which is basically excluding the current rank, the value of the current rank. So these are operations which are often useful in parallel programming. So that's why they are implemented explicitly as functions. Okay, so here's an example of an all reduce. I would say it's pretty straightforward. The only difference with a reduce is that every process is going to have the values. Okay. The interface. Okay, I don't think there's much interesting going on. You have a send buffer, you have a receive buffer, you've got a count and a data type, and essentially that's it. So there is no root. Okay. Then here's an example of an MPI scan. So each process has, again, some values A, B, C. And now what's going to happen with the scan is that the result buffer will actually contain the sum of all the values up to the rank. So basically that means for scan, the result buffer after the operation would be A plus D, A plus D plus G, A plus D plus G plus J, etc. Okay. For an X scan, it would be undefined, then A plus D, etc. So basically, they should be printed here. So of course, you have to be a bit careful if you use an X scan that the buffer, especially of the process 0, is in fact initialized. Otherwise, you might get alt results because if you don't initialize it, anything can be there, and you should be aware of that. Okay, so the whole thing is done in parallel. So that's rather nice for such operations. Of course, you could again implement this using peer-to-peer communication. Would be fairly straightforward to do, but a lot of research has gone into designing MPI scan algorithms that can be run in parallel. So if you're into algorithm design, this is something that I would advise you to have a look at. Various books in which it is explained how you can do a scan in parallel, how you can do an X scan in parallel, and how to do it efficiently. So that has been, and maybe still is, I'm not quite sure, a subject of active research. Okay. There are quite a lot of other collective operations. So for instance, there is an all gather. So as you can guess from the name, that simply means that you have a gather, but the results will be in all of the processes. So you can view essentially an all gather as a gather followed by broadcast. Just as you can consider an all reduce as a reduce followed by a broadcast. Okay. There is also an MPI all to all. So basically, each of the processes have a send buffer, and they send values to individual processes. So process 0 has values 1, B1, and C1. It's going to send A1 to process 0, B1 to process 1, and C1 to process 2. Process 1 has values A1, A2, B2, C2, so it's going to send A2 to process 0, B2 to process 1, C2 to process 2. And same for process 2, which has A3, B3, C3. So at the end of the day, process 0 will have received all the A values, process 1 will have received all the B values, and process C will have received, so process 2 will have received all the C values. Okay, so an all-to-all obviously is a problem. Well, is a problem in the sense that what needs to be sent are in fact n² messages. So basically, the complexity of the all-to-all is in fact n², and there's nothing much to do about that. So this is inherently scaling worse than linear. And that, of course, is a problem if you scale up from a couple of processes to very many processes, because then, of course, n² is going to be quite large. For instance, let's suppose 1,000 processes. Okay, that means 1,000,000 messages. And there's nothing much optimization-wise that you can do. So this scales really, really badly. And so essentially, if you can avoid an all-to-all, you really should consider that, because it's going to scale that badly. Okay. Then, of course, there are also versions of each of these routines with a V at the end. So gather V, scatter V, all gather, etc., etc. And that basically means that each message can have a different count and a different displacement. So basically, you need to specify an array of counts and an array of displacements. And you also have a W version, and then each message can even have a different type. So yeah, again, these are APIs that don't scale. Why not? Well, because basically there is a different count and a different displacement for each member of the collective. So that means those are linear arrays. So that's not going to scale quite nicely. So essentially, again, maybe it's better to try and reformulate an MPI gather V, for instance, in terms of a data structure that actually has the same communication size for all ranks. That scales much better. So many of these operations have, of course, been added back in the days when the number of processes was not so large, and essentially you could live with this. But if you go to thousands of processes, then this is really quite inefficient, and it scales quite badly. So they are essentially to be avoided if possible. Okay, so essentially we had this pass around the ring program to compute the sum of all the ranks. Okay, that was a byproduct of that. Actually, it was not really the goal of it, but let's do the same thing. So let's compute the sum of all the ranks, but now just using an reduce, an MPI reduce. Okay, let's perhaps do that. And let's do that this time in Fortran. So let's call it reduce.f90. Okay, program reduce. And essentially we don't need the size here, so I can just as well remove this. Okay, so essentially this should be it. We initialize a send buffer at each process by its rank. The receive buffer is going to be only used in the root. We specify the message size, message type, MPI integer. The operation we want to do is a sum, so MPI sum. This is the root, which I set constant to 0, and then we have the communicator over which we want to do this collective operation. So everyone is going to call this, no problem, but only the root is going to print the actual result. Of course, it's the only one who actually has something meaningful in its receive buffer. And of course, we can illustrate that. I can set the receive buffer to -1, for instance, and have everyone printed. So print rank, my rank has value, but I want to receive buffer. Okay, so just for illustration, that actually the receive buffer is not being used by the other processes. So MPI F90, reduce, okay, MPI run, MP. So remember, for 4 processes, we should get 6. And indeed, the sum of the ranks is 6, 0 plus 1 plus 2 plus 3. Okay, and only rank 0 actually has a value. Well, the value was changed only in the send buffer of rank 0, not in the others. The others still have minus. Okay, so again, pretty straightforward. We could do the all reduce as well. So then, of course, all values would actually get the value. So let's maybe do that as well. I'm just going to do that in Fortran again, just in order to save a bit of time. So let's edit all reduce 90. Let's initialize that with reduce. Okay. So now I want to reduce. Okay. So of course the signature now is not correct anymore. I think we only need to leave out the root, but let's verify. So in that case, of course, everyone can just print the receive buffer. Can leave that out. And okay, I think it's correct, but let's verify. So MPI will reduce. So for Fortran specifically, we have my all reduce in new style Fortran. C++. Here it is. So we've got our send buffer, we've got our receive buffer. Should be okay. The count, data type, the operation, the communicator. So essentially, that should be the correct signature. So let's try. MPI 90 all reduced. Just a second. There's someone at the door. All right. Sorry about the interruption. They're going to do some maintenance on my security system. So if you hear a siren going off, no worries. I will be surviving that. It's just likely a test. I don't know whether they need to do that or not, but we'll see. So no worries if that happens. Okay. So I'm going to compile that. It compiles. That's always reassuring. Let's see whether it also does something useful. So again, 4 processes with our a.out. And as you can see, every rank indeed gets the result in its receive buffer, and the all reduce has done what it's supposed to do. Okay. So that was again pretty straightforward. There is again an advanced exercise with subgroups, but you can't do that since we don't know what groups are yet. So let's not do that now. Okay. So again, there is a quiz. Feel free to do that, to think about the questions and the answers. And if you have questions about it, let me know. Okay. So in a way, I would say that using collectives is in fact simpler than using point-to-point communication. So in that respect, they are also a help because they reduce the burden on the programmer because the interface is less complex. However, there are of course some more advanced things which we also have to take into account. So let's talk about that a little bit. One of the things is non-blocking collectives. So you might already have seen when I checked the man page of MPI all reduce, there was also an MPI I all reduce, remember? So let's do the man page again. And you see that indeed there is, for the C syntax, for instance, here's the all reduce, and here's the I or reduce. So again, this is non-blocking. So the signature of that function is of course the same, except for the last additional argument, which is again an MPI request. Remember the I send, I receive. Last argument was always a request, so that's the same for collective, non-blocking collectives. Okay. So that basically means that again, we would have to have an MPI wait somewhere. Okay. What we can't do is in one process call a non-blocking collective and a collective call, and in others a blocking collective. So either everyone does an MPI reduce, or everyone does an MPI I reduce, not both. That's not possible. So they must match, and that's a little bit different, of course, than what you have with point-to-point, where you could have non-blocking send in one process and the order receive in another process, or vice versa. So here, every process, if it wants to do a reduce, either does an MPI reduce or an MPI I reduce. Okay. Of course, two consecutive collectives need not be both non-blocking or blocking. You can have a non-blocking MPI I reduce, and then later on in your code, a blocking MPI reduce. That's of course entirely possible. But the corresponding calls must always be to all non-blocking or all blocking. Okay. So basically that means that the collective initiation and the completion are separate. So those calls are again local. They will not synchronize. And then, of course, the corresponding weights will sort of collectively synchronize things the same way that blocking collectives would do. Okay. So again, you can have multiple outstanding collective communications, non-blocking collective communications on the same communicator. That's the exact same as we had with outstanding non-blocking calls. So for instance, you can have several non-blocking sends out there and wait for all of them, for some of them, or specifically for a specific one for each request. Okay. So essentially we have ordered initialization, that's pretty obvious. Then for parallel I/O, we also get a split collective interface. And yeah, that is probably going to be deprecated, but what has been added in MPI 3.1 is essentially non-blocking communication calls. That's something for tomorrow, I think. So basically, let's skip that remark for now. Okay. So there is a progress rule of MPI. So of course, progress on communication is required only during MPI procedure calls. Okay. So that basically means that suppose you have outstanding communication, you do an, for instance, an MPI I reduce, then you do some work, and then you do an MPI wait. The only thing that is guaranteed is that the work will be done as soon as MPI wait exits. But the communication might actually be going on only while you're in the MPI wait call. Okay. But of course, what you want is overlapping communication and computation. So while you're computing, you actually want the communication to go on in the background. because otherwise, what's the point? Okay. So that maybe that may imply that you would have from time to time to call something like MPI test. It means that progress on communication is going on while you do MPI test. That is indeed possible. And you can have additional progress by repeatedly calling MPI test. So that is an option. There are also some non-standard extensions to switch on, and that kind of ensures asynchronous progress. So, for instance, for mpage, you would have an environment variable, mpage async progress set to true, so set to 1, and that would mean that there actually is a helper thread which is taking care of the communication while the main thread is doing the computation. So that's something that you would have to rely upon, but then of course we would have to do something in the MPI init call, which we will discuss later on. Okay. So what are the opportunities? Basically, opportunity to overlap either multiple communication, multiple collectives, that is possible, or communication and computation. But then, of course, you need progress. If no progress is happening, then that overlap is not really happening. So that was discussed on the slide I just mentioned. Okay. Any questions about this? I did some experiments with that, and you can find the code for it in the repository. So that would be likely overlapping computation and communication. And at the time when I did the experiment, just a while ago, I got something like a 10% speed up of my application when I could overlap communication and computation. So it may be interesting to do, but of course it makes your code a little more complex. You would have to check the documentation of your MPI implementation, whether it has something similar that was mentioned, such an environment variable which controls the shepherd thread in order to do the communication in the background. Okay. So an example of why, for instance, a non-blocking barrier might be useful. So that would be MPI barrier. Can we do something with that? Well, actually, yes, we can. So the scenario is the following. The receiver needs information. Okay, that's great. But he does not know the identity of the sending processes, and it also doesn't know the number of sending processes. So we might have, say, 8 processes. Process 0 expects values, but it doesn't know which of the other 7 processes is going to send anything, and even how many processes there are that are going to send something. Okay? And that number, so the number of sending processes, is going to be small compared to the total number. So basically, suppose we have 1,000 processes, okay, only like 10 are going to send, or 11, or 5, but not something like 800. Okay, why is that important? So also what the sender knows, let's finish the scenario first. The sender knows all the neighbors which need some data. Okay, so why is it important that the number of processes that are going to send information is small? Well, otherwise we could just do a getter. But of course, if we have 1,000 processes and only 10 want to send, then basically a gather is overkill, since most of the processes are actually going to send some value. And only a few processes are going to send something that is meaningful. So yes, we could do that with a gather, but it's not going to be very efficient. Okay, so in that case, what can we do? We could, of course, do an all-to-all, an MPI reduce scatter, or whatever, but basically that would not be particularly efficient. And that is somewhere where we can actually use a couple of things. We can use an MPI barrier. Okay, but we also need an MPI probe, and that is basically a way to check whether communication already happened or not. So this is the non-blocking variant, also MPI probe, which is a blocking variant. Okay, so the result of MPI probe is going to be non-zero or true if a message arrived. And notice that we can check on the source and we can check on the tag. Okay, it's going to be false otherwise. Okay, that only means that currently there's no such process, no such message coming from source with the given tag on the given communicator. Okay, so now what can we do? If we have a non-blocking barrier, then this is a potential solution. Okay. Each process that acts as a sender is going to loop over its neighbors, sending data with MPI synchronous send. Okay, so basically it will be able to determine whether the receive has started or not. It's a non-blocking call. Okay, then we have a loop. If a process is in the role of a receiver, then it's going to do an MPI probe. So basically, it's going to check for MPI any source, MPI any tag on that communicator if there is a message received. If the message is received, it's going to do a blocking MPI receive. So it's immediately going to get that message. And of course, from the status, from the envelope of the message, it can determine the source and the tag if it needs to. Okay. So on the other hand, if the process is a sender, then it's going to check whether all outstanding ISend calls, the synchronous calls, are completed. Okay, so that's essentially an MPI test. Okay, if that's done, if all are completed, then it's going to start an MPI barrier. So basically, it signals to all other processes that all the ISends for this process have already been received by the receivers. Okay. All right. Then we are looping, and we are going to loop until everyone reaches MPI barrier. MPI barrier. Okay. So essentially, we are going to test with an MPI wait. With an MPI test, whether that's already done. If that's not the case, then of course we loop again. So if everyone reaches the MPI barrier, then of course we know that all the sends have been received, and so our communication is done. So that's an elegant way of actually solving this particular pattern. And we will see other ways to do that along the road, but this is the first one. So that is something that is again sort of a recurring example, like the halo exchange. So in the code, the sparse sense here, there are some implementations. So let's have a look. So for instance, there is an implementation with an I barrier here in Fortran. There is also there are also other implementations, as you can see. One is with one-sided communication, the other uses an reduce. But let's have a look at the sparse sense example with the I barrier. And you see, basically, we have quite a lot of variables declared, but the pattern here is we set up everything as usual. Then we get some value. This is basically to determine the senders, essentially. So I'm going to send messages based on something here. Okay. Yeah, here I'm just determining a seed for my random number generator, and I'm doing a hash here based on the rank. So yeah, maybe something that I should mention, when you're doing MPI, don't use, for instance, time as your seed, because it might be that several processes have the same seed. That's typically not what you want. So make sure that your seed is unique, and yeah, you can do a little hashing algorithm, such as I do here, in order to ensure that you get an unique seed here per rank. That's some code I stole from somewhere. That should be a good enough hash in order to get random seeds that are different per rank. Okay, so basically, I also set a probability for things to send, but here you see the do loop. So I'm going to send multiple times, and yeah, this is not so easy to see what's going on here. The code is basically too long. That is the problem. But here you see the MPI synchronous sense. So in this particular case, I'm going to do things a little differently, because in this case, I'm just relying on the completion of the synchronous send here. So basically, the simplification which I make with respect to the slides is that actually only that the receiver is in fact, there is only one receiver. So that on the one hand simplifies things a little bit, because I can get away with just using an blocking synchronous send. So that simplifies the code a little bit. So there is only a while loop on the receiver's end, not on the sending end. The sending end is just sending all its messages, and it is going to call the MPI barrier. So it will only reach the MPI barrier when all its messages are sent anyway. So there is no loop needed here. Okay, and then there is one process that receives, and this is of course looping, and it's going to test whether the barrier has been reached or not. Okay, so in that respect it's a little different because it's going to there's only one receiver here. Simplifies things a bit. Apart from that, it's the exact same thing. Okay. So basically, this is more or less a graphical representation of what happens, but I think it's fairly clear what is going on here. Right. Then there is also collective operations for intercommunicators, but of course let's mention that only when we have talked about intercommunicators, which basically will come later on today, I expect. Okay. Sparse collective operations on process topologies. So basically, you can do a neighbor all together, a neighbor all to all. So that's not so much an all to all or an all together on all processes, but only on neighbors. And those neighbors are defined by a virtual topology. And that's something that we will talk about today, what virtual topologies are. So remind me to get back to that concept later on when we have actually talked about virtual topologies. Okay, so basically what we can use additionally is MPI in place, and that can come anywhere where there should be a buffer. So for instance, in gather, at the root process, the send buffer doesn't have any meaning. I can put there MPI in place. And of course, the receive buffer can also be MPI in place in every process that's not the root. So basically, for scatter, for instance, the receive buffer is MPI in place, which basically means that it ensures that no message is sent that is actually done. It's not overwritten. Okay, so this can be useful from time to time with reduce or reduce operation and so on. Okay, so that's just mentioned. Non-blocking barrier. So what's the idea here? Yeah, so essentially that is the code which I just showed you. So and this we know. That's an exercise that we are not going to do in this case. We may do it later, but not now. Okay, again a quiz. And let's do error handling because it's pretty short, and then we can have a lunch break. And then after lunch we'll talk about groups and communicators and virtual topologies. And then most likely I'm going to skip over one-sided communication and shared memory now and do derived data types and perhaps also parallel file I/O. And then tomorrow we'll revisit one-sided communication and shared memory programming. I prefer that order because you're not that likely to use one-sided communication or shared memory programming with one-sided communication. So I prefer to concentrate today on things you're definitely going to use, and that's derived data types and probably parallel file I/O. Okay, so let's talk a little bit about error handling, and essentially we can be pretty brief on that. Basically, there are error codes and new in MPI4, the error classes. So most important aspects, basically, communication should be reliable. So normally, if something starts going wrong, there's nothing much you can do. Basically, if there is a problem, there are of course no guarantee of what is going to happen. So by default, you will just abort. And that happens if the MPI library detects an error, it's just going to abort everything. So if it does not do so, then basically you would have rather unpredictable behavior, and that would be not so nice. Again, just give me a second. I'd like to ask something of the person who is doing the maintenance. Okay, again, apologies. As we already mentioned, every MPI routine basically returns an error value, but yeah, you're not going to do anything with that, because basically if something fails, then you're in an undefined state anyway, and that is not going to be recoverable. So essentially, you can't do much except calling MPI abort. And that's likely going to be done by the MPI library anyway. So yeah, that doesn't make much sense essentially. So the only place where error handling is actually useful is in MPI IO. And there, the MPI errors are actually returned. And of course, there you can do some proper error handling. So basically, for instance, you could say, well, okay, suppose I'm opening a file and that fails for whatever reason, then you might do something else. For instance, reading a default file or something like that, or assuming that settings which were stored in that file are in fact the default ones, whatever. Okay. So that's typically what you do with respect to error handling. And that brings us to the end of it. As I mentioned, it was a really, really short chapter. Okay, so basically, now groups, communicators, and so on. So we only have 10 minutes left. So that's perhaps not so useful to start now. So one of the things we could do is start on this exercise here. So the non-blocking barrier solutions thing. Okay, let's perhaps do that in C again. Let me. Okay, no more editors open. Again. All right, so I'm going to call that sparse send, for instance. Okay, so as usual, include stdio. Okay, so we will probably also want to do some random stuff, so let's also include standard lib, which contains the C random number generator. Okay. So again, it's easier if we just set a target destination, so target rank. So let's call that 0. So 0 is always going to play the role of receiver. Again, this is just to simplify things a little bit. And actually, well, okay, maybe let's do the full example of everyone being a receiver and everyone being a sender. Okay, maybe that's better. Okay, so we determine whether we are, no, everyone is a receiver. So essentially, that means that the receiver is going to do the I probes. So we are going to do a loop, which is an infinite loop. Okay. Then we are going to be the sender. So that basically means everyone is going to be, and that sender is going to send something. Let's say an integer. So send buffer is just going to be my rank. Okay. We also need receive buffer, so let's declare that. And then, of course, each process is going to send to a number of other processes. So let's say, for instance, that for integer destination is 0, destination is less than my size, destination plus plus. If random, this is an integer, so if we divide that by rand max, if this is less than a certain fraction, then we actually send something, but we need to do an asynchronous send. So and that probability should be a bit lower. So let's set that to 0.1. So that makes sure we have sparse sends, not so sparse, because still 10th of the process is sending, so that would be 100 out of 1000. But okay, so this should be an asynchronous send, a non-blocking send, but send. Okay, so essentially that means we need a request. And actually we need many requests, so basically we need as many requests as we do sends. So then of course the question is, how are we going to represent those? We need an array. So that means we need int number sent messages, which is of course 0. Okay. And we also need an array of requests. And of course, there are more intelligent ways to do this, but let's say that we simplify life a bit. We have as many requests as MPI size. Okay. This we can't really do, so we should make that a pointer. and do an allocation. So the request is MPI request pointer malloc, MPI request, etc. Oops. Okay. So now we can put the requests. Let's not do it this way. Okay. Let's clear that it's an array. Just one thing. Okay, and we have MPI isend. Okay, so basically we've got requests. And that is number of sent messages plus plus. Okay, and of course this needs to be an address, so I need to add this. Okay, so basically that means after the call, after all the messages have been sent, I know how many messages have been sent, and I've initialized all the requests appropriately. Okay, so that takes care of that. And now, of course, I can start doing a loop over the requests and testing whether they are actually all done or not. Okay, so there are several ways to do that. Given that I have an array of requests, I can use an MPI all wait. But that would not be my best idea here. Okay, let's continue in the afternoon. Let's continue in the afternoon, and let's break for lunch now. Let's take an hour lunch break as usual, so till 1. If there are any questions, feel free to put it in the chat. Okay.